All moving parts in an engine require lubrication. That is, the application of oil to moving parts to reduce friction between them. A lubrication system distributes oil through the engine. A typical lubrication system consists of an oil sump, an oil pump, and oil galleries. The oil is stored in the sump, bolted to the bottom of the engine block. Oil is drawn from the sump by an oil pump. Oil galleries are small passages in the cylinder block that direct oil to the moving parts. Oil that has been pumped to the crankshaft main bearings travels through oilways to the connecting rods. Oil may also be splashed from the connecting rods onto the cylinder walls. A filter is usually provided to remove particles of dirt from the oil, and the circulation of the oil assists with the cooling of the internal parts.
Most small four-stroke petrol engines use what is called splash lubrication. On horizontal crankshaft engines, a dipper on the bottom of the connecting rod scoops up oil from the crankcase for the bearings. In this engine, it's also able to splash oil up to the valve mechanism. Alternatively, an oil slinger can be driven by the camshaft. A similar system is used in most small vertical crankshaft engines. Oil is also splashed up to the valve mechanism.
Modern vehicle engines use a pressure or force feed lubrication system where the oil is forced around the engine under pressure. Let's look at gasoline engines first. Oil won't flow up into the engine by itself, so a pump collects it through a pickup tube and a strainer, and forces it through an oil filter, then into passageways in the engine block called galleries. The galleries allow oil to be fed to the camshaft bearings, the valve mechanism, and the crankshaft main bearings. Holes drilled into the crankshaft webs allow the main bearings to supply oil to the big end bearings. After circulating through the engine, the oil falls back to the sump to cool. This is called a wet sump lubrication system because the oil is kept in the sump ready for the next time it's used. Some special engines use a dry sump lubrication system. It uses all of the parts that make up a wet sump system, and it lubricates the engine in the same way. It differs from the wet sump system in the way the oil circulates. In a dry sump system, the oil falls to the bottom of the engine into an oil collection pan. A scavenge pump then pumps it to an oil tank where it is stored until the normal oil pump collects it and pumps it through the filter and engine in the normal way. Because there is no oil storage sump under the engine can be mounted much lower than in a wet sump system. The oil tank can be positioned away from the engine where it can get best cooling, and the amount of oil in the system can be much greater than in the wet sump system. Diesel engines are lubricated in much the same way as gasoline engines, but there are differences. Diesel engines typically operate at the top end of their power range, so their operating temperatures are usually higher than those in similar gasoline engines. So the parts in diesel engines are usually more stressed. As a result, diesel oils need a different range of properties and are classified differently. It's common for some diesel engines to use an oil cooler to cool the oil in the engine. The cooler and oil filter are usually on the same mounting on the cylinder block.
Most two-stroke gasoline engines use a set gasoline-oil mixture for lubrication. There are different kinds of oils and gasoline oil mixtures. They must be used according to the manufacturer's specifications. For small two-stroke engines, the oil and fuel are pre-mixed. A mixture of air, oil, and fuel passes through a sealed crankcase on its way to the combustion chamber. That makes the crankcase part of the fuel intake system, so it can't be used as a sump. As the air, fuel, and oil enter the crankcase, the fuel evaporates, leaving behind enough oil to keep parts coated and lubricated. The crankshaft and connecting rod bearings in two-stroke engines are ball and roller types. Because the parts of this kind of bearing only roll over each other, they only need a minimum of lubrication. Some two-stroke gasoline engines use an oil injection system. This system doesn't need the oil and gasoline mixed manually. An engine-driven oil pump takes oil from a tank and pumps a measured amount directly into the engine, where it will mix with the fuel and lubricate the internal engine parts. The pump delivers the correct amount of oil for the engine speed and the throttle setting, which makes it a more precise system than running the engine on a fixed oil-gasoline mixture.
The rotary engine lubrication system is similar to that of a four-stroke petrol engine. An oil pump picks up oil from the oil pan through a strainer and delivers it to an oil cooler on the front of the engine. The oil cools, then enters the oil filter at the rear of the engine. A regulator valve controls the oil pressure in the system. The oil goes onto the main bearings and rotor bearings and is sprayed into rotor cavities. Along the way, it absorbs heat, then returns to the oil pan. A bypass valve at the end of the eccentric shaft helps the engine warm up. When the engine is cold, it stays open and sends oil from the shaft to the oil pan and stops it spraying on the rotors. As the engine heats, the valve starts to close. Pressure in the shaft builds up, and cooling oil starts to spray on the rotors. The rotary engine uses oil injection. A pump sends oil to oil nozzles in the intake manifold and to oil nozzles in the intake passages in the rotor housings. Oil from these nozzles goes to the engine and lubricates the rotor seals. If the engine has a turbocharger, oil lubricates it as well.
One function of a lubrication system is to reduce friction. Friction occurs between all surfaces in contact. When moving surfaces come together, friction tends to slow them down. Sometimes that's just what's wanted. Friction can be useful. But it can also cause serious damage. It can make metal parts so hot they melt and fuse together. When that happens, an engine is said to have seized. How long an engine lasts depends to a large extent on how well it's lubricated, especially at the points of extreme loading. So lubrication reduces unwanted friction and controls it where it is useful. It reduces wear on moving parts. Clearances fill with oil so that engine parts move or float on layers of oil instead of directly on each other. Much less power is needed to move them, and that's a plus. It helps cool an engine. It collects heat from the engine, then returns it to the sump where it is cooled. It helps absorb shock loads. A power stroke can suddenly put as much as 2 tons force on main bearings. Layers of oil cushion this loading. Oil is also a cleaning agent. It collects particles of metal and carbon and carries them back to the sump. Larger pieces fall to the bottom.
For oil to do all of the work that's expected of it, it must have special properties. Its viscosity is crucial. Viscosity is a measure of how easily a liquid flows. Low viscosity liquid is thin and flows easily. High viscosity liquid is thick and flows slowly. Lubricating oil must be thin enough to circulate easily between moving parts, but not so thin that it will be forced out from between them. If it is forced out, parts will be left in direct contact and they'll be damaged. If it's too viscous, it moves too slowly to protect parts, especially in a cold engine. It was once normal practice for engines to need one grade of oil for summer and another for winter. Oils are graded or classified by the American Society of Automotive Engineers, or SAE. An engine oil with an SAE number of 50 has a higher viscosity or is thicker than an SAE 20 oil. Oils with low viscosity ratings, say SAE 5, 10 and 20, were tested at a low temperature, around 25.2 degrees Fahrenheit or minus 18 degrees Celsius, and were used for cold conditions. Oils with high viscosity ratings, say SAE 20, 30, 40 and 50, were tested at a high temperature, around 210 degrees Fahrenheit or 99 degrees Celsius, and were used for hotter conditions. Modern oils, however, are blends of oils which combine these properties. The oils are blended with additives called viscosity index improvers to form multigrade or multi-viscosity oils. They provide better lubrication over a wider range of climatic conditions than monograde oils. Oil is also classified by the American Petroleum Institute, or API, service classification. Oils for spark ignition engines carry a prefix S, and diesel or compression ignition engines use C. Some oils have additives that make them suitable for both. Manufacturers recommend which viscosity and API classification is ideal for a particular engine.
Special chemicals called additives are added to the base oil by the oil companies. Different combinations of these additives allow the oil to do different jobs in an engine. Extreme pressure additives coat parts with a protective layer so that the oil resists being forced out under heavy load. Oxidation inhibitors stop very hot oil combining with oxygen in air to produce a sticky material like tar that clogs galleries. Corrosion inhibitors help stop acids forming that cause corrosion, especially of bearing surfaces. Anti-foaming agents reduce the effect of oil churning in the crankcase and minimize foaming. Detergents reduce carbon deposits on parts like piston rings and valves. Dispersants collect particles that can block the system, separate them from each other, and keep them moving. Then they will be removed when the oil is changed. The sump is bolted to the engine under the crankcase. It is a reservoir or storage container for the engine lubricating oil and a collector for oil returning from the engine lubricating system. The sump can be formed as a thin sheet metal pressing and shaped to ensure that oil will return to its deepest section. The oil pickup tube and strainer are located in this deep section to ensure they stay submerged in oil and to prevent air being drawn into the oil pump. Some high-performance vehicles have a windage tray fitted to prevent churning of the oil by the rotation of the crankshaft. Baffles prevent oil from surging away from the pickup during cornering, braking, and accelerating. The sump's large external surface area helps heat transfer from the oil to the outside air. In some designs, the sump is an aluminum alloy casting with fins and ribs to assist in this heat transfer.
The oil collection pan is part of the dry sump system which is used in some motorcycles. It replaces the sump in the wet sump system, but it is much smaller. It collects the oil after it has circulated through the engine and directs it to the pickup strainer on the scavenge pump. Since no oil is stored in the engine in this system, a dipstick that is normally used to check oil levels in the sump is not needed. The oil tank is part of the dry sump lubrication system. It is usually positioned away from the heat of the engine, and the large surface area improves cooling. It receives oil from the scavenge pump and allows it to settle and cool. The main oil pump then pumps it back through the lubrication system. A dipstick is often provided to measure the oil level.
There are two basic oil filtering systems, full flow and bypass. The full flow type filters all of the oil before delivering it to the engine. The bypass type only filters some of the oil. The full flow type is the more common. Its filter uses pleated filtering paper in a metal housing to collect harmful particles. Normally, all oil goes through the filter before it gets to the engine, but if the filter clogs up, it can starve an engine of oil. As a safety measure, full flow filters have a bypass valve. If the filter clogs, this valve opens and directs unfiltered oil to the engine. Dirty oil is better than none at all. Most oil filters on diesel engines are larger than those on similar gasoline engines, and some diesel engines have two oil filters. Diesel engines produce more carbon particles than gasoline engines, so the oil filter can have a full flow element to trap larger impurities and a bypass element to collect sludge and carbon soot. In a bypass system, the bypass element filters only some of the oil from the pump by tapping an oil line into an oil passage. It collects finer particles than a full flow filter. After this oil is filtered, it goes back to the sump.
Between the sump and the oil pump is a pickup tube with a flat cup and a strainer immersed in the oil. The strainer stops large particles of dirt and carbon entering the pump and damaging it. The pickup tube leads to the inlet of the oil pump on the low pressure side of the pump.
Oil pumps may be driven from the camshaft or the crankshaft. In a rotor-type oil pump, an inner rotor drives an outer one. As they turn, the volume between them increases. This larger volume lowers the pressure at the pump inlet. Outside atmospheric pressure is then higher. This forces oil into the pump, and it fills the spaces between the rotor lobes. As the lobes of the inner rotor move into the spaces in the outer rotor, oil is squeezed out through the outlet. The crescent pump uses a similar principle. It is mounted on the front of the cylinder block. The inner gear is on the end of the crankshaft, which then drives the pump directly. An external toothed gear meshes with this inner one. Some gear teeth are meshed, but others are separated by the crescent-shaped part of the pump housing. The increasing volume between gear teeth causes pressure to fall. Oil is then taken through the intake port and carried around between the gears and crescent, then discharged to the outlet port. Similarly, in a geared oil pump, the driving gear meshes with a second gear. As both gears turn, their teeth separate, creating a low-pressure area. Higher atmospheric pressure outside forces oil up into the inlet. The spaces between the teeth fill with oil. The gears rotate and carry oil around the chamber. The teeth mesh again, and oil is forced from the outlet toward the oil filter.
A normal pump is capable of delivering more oil than an engine needs. It's a safety measure to ensure the engine is never starved for oil. As the pump rotates and engine speed increases, the volume of oil delivered also increases. The fixed clearances between the moving parts of the engine prevent oil escaping back to the sump, and pressure builds up in the system. An oil pressure relief valve stops excess pressure developing. It's like a controlled leak, releasing just enough oil back to the sump to regulate the pressure of the whole system. Pistons, rings and pins are lubricated by oil thrown onto the cylinder walls from the connecting rod bearings. Some connecting rods have oil spurt holes. These holes are positioned to receive oil from similar holes in the crankshaft. Oil can then spurt out at the point in the engine cycle when the largest area of cylinder wall is exposed. It lubricates the walls and gudgeon pin, and also cools the underside of the piston. Oil feeds to the cylinder head and through a gallery to the camshaft bearings and valve train. As well as lubricating these moving parts, it also gathers heat from the engine so its temperature keeps rising. Finally, it drains back to the sump to cool and start again.
If a lubrication system fails, it's serious, so it's crucial to know it's working. If oil pressure falls too low, a pressure sensor in a gallery can light up a warning light or register on a gauge. Low oil pressure can mean a lack of oil. It may have leaked away. Or it may have been burned. This can be caused by worn piston rings which let oil into the combustion chamber. Some engines even use an automatic cutout that turns off the engine if oil pressure falls too low. Too little oil in the engine is a problem, but so is too much. The crankshaft can whip it into foam and cause leaks by flooding the seals. Of course, the simplest indicator of oil level is still the dipstick.
Engines which operate under severe conditions may use an oil cooler to cool the oil in the engine. In diesel engines, the oil cooler and oil filter are often on the same mounting on the cylinder block. The oil cooler is a heat exchanger. It transfers heat from the oil to coolant from the cooling system. Coolant circulates through tubes in the cooler, and oil fed from the lubrication system surrounds the tubes. As the coolant circulates, heat is removed from the oil. In another design, the oil cooler is mounted in the airstream at the front of the vehicle. This type of oil cooler uses the flow of air passing across its fins to cool the oil circulating through it. It is called an oil-to-air heat exchanger.